going up. So my original function goes down, p goes down, and then p goes up, which means I have found what? A local minimum, right? How do I know this is the only minimum, though? Well, because in order to have another minimum, I know the graph goes like this, right? I have a lowest point. I know there's no other lower point because it would have to come back down and then turn back up, and this is all it ever does, right? It goes down and up one time. And so that has to be the only minimum I have. Okay? So from that, I can say we have a minimum when x equals 6.1, right? And then what is y then, right? This is one dimension, but you need the full dimensions of the enclosure. So what would y be? Go back to your constraint. What was the definition we had for y? Was it 50 over x? Yeah. It was 50 over x, right? 50 over, so I divide by the 6.1. Someone do that for me, please. 50 divided by 6.1 is approximately 8 point what? 8.2-ish? Okay, close enough. There you go. So if I make this 6.1, 6.1, 6.1, 6.1, and make this 8.2, then I will have an enclosure that has an area of 100 square feet, and I will use the least amount of fence possible. If I build it any other way, I'm going to spend more money on fence. Okay? How are we doing? Are you getting the basic idea of this? I mean, each problem is different. I don't want you to get the impression that all optimization problems are fences being built. That's not what it is, all right? Optimization is very generic. We just like to always give these problems to start because they're kind of easy to visualize. Let's see. Where do I want to go? How much more time do I have? I think we can go to 10:20. For those of you who might have come in late, we're taking a quiz, right? In a little while. All right, let me see here. A can must hold 1 liter. 1 liter is 1,000 cubic centimeters. Find dimensions which minimize surface area. This is a really classic problem, very applicable to the real world. So I'm going to draw a picture. Okay, I want to put here, see image below. See image. All right, so I need to draw you the can, all right? What I mean is what we call a right cylindrical can, like a soda can, beer can, whatever you prefer, all right? We want to create a can, all right? And we're not accounting for, you know, on soda cans, there's like, you know, they're not perfect cylinders, right? They have like a little divot on the bottom and they're not perfect. Okay, but this is just theoretically, let's just go with a perfect cylindrical can. Let's say we want to make this, right? If you wanted to account for all the unique shapes of a can, then it would be more complicated. And that's what, in the real world, that's what they would do. They'd have to count for every little detail of the can. Here, we're just going to do this. All right, so I want this to hold 1 liter, right? There's an infinite number of ways I could do that. I could make a can that looks like this. Almost like a beaker. Real tall, right? Real tall can, you'd be drinking like this, right? But really, really small. That could hold 1 liter, right? Or I could do another extreme where I do something like this, where it's almost like a disc, right? And you're like drinking out of this huge disc, right? I could make both of these hold 1 liter, right? And there's everything in between. So the question is, how do I do this so that I use the least amount of surface area? Surface area is basically like the aluminum you're going to need to make the can. The amount of aluminum required for this, for the surface, is a lot less than the amount of aluminum used for this, right? Because this has this huge piece. But there's an optimum way to do this. There's a way to minimize the surface area and thus minimize the cost of making the can. Understand that? So we need to figure out what the dimensions of this can need to be in order to get the least amount of material to make the can. So what is our objective? What is the thing we're trying to either find the max of or the min of? Surface area. I'm going to put SA for surface area, right? Not San Antonio. Surface area. Okay, surface area equals. All right, I need to write the surface area down. Do you all know what the surface area of the can is? So I see you looking in at formulas, right? I don't think it's there. So look, sometimes in math, it's better to not try and memorize something and just think through it. So watch this. I don't actually remember what it is right off the top of my head, but I can create the formula pretty easily. So if this can, let's say this can has a certain radius, I don't know what it is, R, and a certain height, let's call that H, all right? Would you all agree with me that the top of the can and this bottom of the can are just circles? And you know the area of a circle? What is it? Pi r squared, right? So we have, if this is R, the radius, then the area on the top and the area on the bottom, that's pi r squared, and we have 2 of them, top and bottom. So you all agree, first of all, we have 2 of the pi r squareds. Yes? Now, the next part is a little bit harder, but imagine you've got this can, right? We just accounted for the area on top and the area on bottom. Imagine now that you take this can and you cut it open, okay? You cut it open and you lay it out flat like this. Then this area was the area of that outside cylinder, wasn't it? Okay, this is just a rectangle. How tall is it? Well, in terms of our can, it's H, isn't it? So let me just draw that picture. This is that thing cut open. This from here to here is H, right? We took it, we rolled it open like this. That's H. What's the distance from here to here, though? It's the circumference, right? Because it's the distance around this. It's the circumference of the circle, and circumference is 2 pi r. That's your circumference. So this distance from here to here is that circumference, so that's 2 pi r. So then what's the area of this? 2 pi r times h, right? So we had the top and the bottom, which was the 2 pi r squared, plus the area of this thing opened up, which was 2 pi r h. That is your surface area formula for a can. Got it? On a test, I wouldn't give you something like that where you have to go deduce that yourself. I would provide you the formula, or it would be on your formula sheets. All right, right now, our surface area requires that I know the radius and the height, right? So like kind of like we had the x and the y, now I have r and h, yes? I would like to, if possible, get this down to a single variable. So I need a constraint. Do we have a constraint? We have to hold a liter, right? How much the can holds is called the volume of it, right? The volume. So I know that the volume must be, and we don't put a liter, we put 1,000 cubic centimeters. 1,000 cubic centimeters is our volume. And then I need a formula for the volume of a can. So do you all know how to find the volume of this? It's actually pretty easy. You take the area of the top surface. What was the area of this? Pi r squared, right? And you multiply how deep it is. So pi r squared times h will give you the volume. And that is on your formula sheets, I believe. The volume is pi times r squared times h. That must be 1,000. Do you see I have a second equation over here that has both variables in it, r and h? Just like we had before with the enclosures, we had something over here that had x and y, and we solved for y. Here, I'm going to take this, and what do y'all want to solve for? We have choices. You want to solve for r? So if you solve for r, do you agree I'm going to have to take a square root at some point? Do you want to take a square root? Probably not, right? If we solve for h, we never have to take a square root. So it's probably best if we solve for h here. How would I solve for h? Divide by pi r squared. That gets plugged in over here. Surface area, can I stop writing SA and just put A instead of SA? I'm just going to put A instead. So that, let's get rid of that, let's call it A for area. This area of this can is going to be 2 pi r squared plus 2 pi times h. H is 1,000 over pi r squared. I'm going to go one more, maybe two more steps. The area here is 2 pi r squared plus, over here we get pi's that cancel, right? Pi's that cancel. And then the 2 hits the 1,000 and becomes 2,000. And on the bottom you have r squared. Am I missing an r? Oh, I am missing an r. Man, I'm telling you, this week is amazing. All right, I'm missing an r in there. 2 pi r times 1,000 over pi r squared. I was missing that r right there. So that actually changes things because one of the r's goes away as well. So the pi cancels, one of the r's cancel. I've got that. Did I? No, yeah, the 2 hit the 1,000. I'm going to have to retire soon, I think. All right, good? Do we have the area as a function of a single variable now? We do, right? So I could actually call this like A of R if I want. What's the next step? Next step? Domain. Is it closed or open interval? Think about R. R is the radius of the can. Can the radius be 0? If it's 0, then what would the volume be? If the radius of the can is 0, what's your volume? 0. But the can must hold what? 1,000 cubic centimeters or a liter. So you can't let the radius be 0 so you don't have any volume. So you could have a really narrow, right, narrow can, or you could have a really, really wide can. How wide? There's no restriction. Yes?
Could you also determine that by plugging in 0 into...
Yeah, you can see here that you can't plug 0 in for R, right? Can't plug 0 in for R, right here or there, right? So you can do it that way as well. I just think thinking about the geometry of the problem helps.
So if you can't put 0 for R, then that would determine that
it's open interval, yeah.
But if you could plug in 0, then that would make it closed.
As long as there's no other places that would cause division by 0 or something like that. Square root of a negative number. All right, there it is, yes? Very similar to the last problem. So I'm going to offer this to you as a bonus to finish and bring to class next time we meet, all right? So what I want is at the very end is R equals some number, decimal, do decimal, it's much easier, and then H equals some number, all right? Understand? You have to take derivative, right? Set it equal to 0, figure out where it doesn't exist, get your critical numbers, number line, right? Test points, up, down. What are we looking for? Up, down, or down, up here? Minimize surface area. We're looking for down, then up, right? Down, then up. All right. Homework. For homework, I'm going to tell you to just do you should just try these, see how it goes. Try number 11, number 12. This is out of 4.5. Try 11 and 12. Number 25 is tough, but you can try 25 if you want. Oh, and number 9. Sorry, number 9. Number 9 has a farmer that's building a pen, a couple of pens. See what you can do on that. All right, quiz time. I'm gonna turn the camera off. We don't need it for this. So if you